Hi, I'm Luca, and welcome to this episode of Do It Right, Dynamic Hydronic Balancing. In previous episode, we discussed the interaction of dynamic control valves with the terminal units in a hydronic system. Today, I would like to explain to you the interaction with pumps. Pumps are the pulsing element of a hydronic distribution system, almost like a heart. And in the past, before dynamic valves were invented, most commercial pumps for these kind of applications were fixed-speed pumps, which means the same volume of water was circulating in the whole building the whole time. And if a valve closed one coil or a group of them, the water was simply diverted and sent back to the return pipe through bypasses. And from an energy efficiency standpoint, this is the worst condition possible, because you always use 100% of the water, even when it's not needed. And this is obviously a big waste of energy. And an additional effect of having a constant volume system is the potential for a less than desirable delta T. In fact, the water that has been diverted will not transfer the energy it is carrying to the space, resulting in the energy being carried back to the boiler or the chiller. On the other hand, the same pump has an intrinsic great saving potential. In fact, if you consider that the electrical power absorption of a pump has this type of relationship with its speed, then it's clear that by reducing the speed by a half, you can reduce the corresponding absorbed power down to 1/8 of the original value. And variable speed pumps started to become popular thanks to this energy-saving potential. However, after their introduction, new problems came out because of their combination in hydronic systems with all standard control and manual balancing valves. I would say that combining a dynamic pump with a manual balancing device and a standard control valve was a first step, but not yet the perfect combination. And this is why dynamic balancing valves, like PACV, have been developed and are the best solution for the latest state-of-the-art pumping technologies. By the way, Siemens introduced the first PACV to the global market in 2000, and thus started the birth of mass production of PACVs. So with this kind of dynamic valves, pumps can easily adjust to the ever-changing system demand, which is determined by the number of terminal units that require thermal energy. When all the units are open, the pump runs at its maximum design point. But when the system runs a partial load, which means some of the valves are closed or they are in the process of modulating the energy, the pump feels this change in the system and it can reduce the speed accordingly to adapt to the new conditions. Because systems rarely operate at design conditions, and more than 90% of the system operations will occur at partial load. And when this happens, it means that the pressure available across the remaining open terminal units changes. And here, during partial load, our dynamic balancing valves play their fundamental role by automatically adjusting the internal elements in order to maintain the optimal flow rate the coil requires. And the beauty of this process is that it works under all load conditions, and even if the actuator is modulating the valve. In fact, in that case, the dynamic valve will still be able to avoid any influence of the changing pump head, and the only effect the coil will see will be the reduced flow as determined by the actuator movement. But how can the pump be so smart to feel that the hydronic system is changing its thermal requirement? We will see this in the next episode, where we will talk about how to commission a dynamic hydronic system. Thank you for watching. Do it right, dynamic hydronic balancing.